to the Institute of Astronomy. I think it's going to be clear, or at least we're going to make a go of it. The weather forecast said cloud, but the sky disagrees, and so we're going to go with what the real sky is doing. So our observers on the lawn are setting up for you. So for anyone that hasn't been here before, or hasn't been here on a clear evening, the plan is you have the talk, and then we lead you out onto the lawn afterwards for some stargazing. There will be some observers on the lawn with a bit of a floor show, and there will be some people in the domes showing you different objects. But before that, we have our headline speaker. We have George Vasilakis, who is a PhD student here in Cambridge and also came to us from working at NASA as an intern. And he's going to be telling us all the interesting details that happen when NASA plans space missions. So, George.
Thank you. Can everybody hear me? Everyone can hear me all right? All right, sweet. So, thank you for the introduction. I'm George. I'm a first-year PhD student in the Institute of Astronomy here at Cambridge. And I will be telling you today about how NASA spends $10 billion on telescopes and makes them into reality, right? Okay, so first, NASA generally takes big science questions and turns that into real spacecraft that take images like the beautiful pictures above. So on the left-hand side, we have a picture from the Hubble Space Telescope in 2014, and on the right, the brand new James Webb Space Telescope. It translates science into direct and efficient engineering guidelines to create some of the most complex telescopes ever created. And before we can go into how NASA does this, we can ask the 4 W's. So what is NASA? Who is NASA? Why is NASA? Et cetera. So what is NASA? So NASA is the United States of America's Civil Space and Aeronautics Agency. It builds and runs everything from sending robots to other planets like Mars and Venus, to telescopes that see the early universe like Hubble and James Webb, and also that satellites that watch Earth. NASA takes human ingenuity and willpower and engineering to turn all of that into data and discoveries. So why is NASA, right? Why does NASA exist? So NASA was born in 1958 when President Dwight D. Eisenhower saw Sputnik, the Russian satellite, launch their first satellite into space. It was an effort to consolidate all of the United States space research might into one organization with proper funding, proper organization, and management. Today, the space race doesn't exist anymore. But the reason that NASA still matters is because it tackles large projects that are too big, too risky, too expensive, too long-term for any single company to do, right? We can't take the Hubble Space Telescope and turn a profit. It's not commercialization that we're after for. It's the universe's deepest mysteries, right? Where is NASA, right? NASA is all across the United States. When people think of NASA, they think of Houston. We have a problem, right? And that's fair. That's fair. Because the International Space Station astronauts do communicate directly with Houston. But there are NASA centers all over the country. We have Houston here, highlighted in green, at the Johnson Space Center. Another great example is in red here at the Cape Canaveral Kennedy Space Center. This is where most of the rockets launch. It's where the Apollo missions launched from. It's where the next astronauts who go to the moon in the Artemis mission will launch from. And then I worked at the Jet Propulsion Laboratory in Pasadena, California, where they do lots of robotics and lots of telescope optics. So, and yes, if you're wondering, I got more vitamin D in California in one summer than I probably will in my entire PhD here at Cambridge. But I had an excellent time, and I will have an excellent time here. So who makes NASA happen, really, right? It isn't one big building, as I just showed. It's distributed across the entire country of America. It's a team sport. So scientists define the questions that we need to ask. Engineers build and test that hardware. Operations team and projects teams manages everyone, keeps the telescopes running. And partners in industry, universities like Cambridge, and also international collaborations make the entire organization work. So NASA itself is about 18,000 civil servants. But the real workforce is much larger because NASA doesn't work alone. They contact with industry, and technically the Jet Propulsion Laboratory, which I just said I worked at, is a contract and has about 6,000 employees. Here are 500 interns, as we were posing for one photo in the summer. I'm in the big red arrow, smiling in my sunglasses. For the James Webb Space Telescope, for example, it took over 20,000 people globally to create this mission that was over $10 billion and has revolutionized our understanding of astronomy. So now that we understand what, why, who, we can get to how, right? How does NASA turn a spacecraft, how does it turn an idea into a spacecraft that revolutionizes astronomy, right? First, you have to ask a big science question about the nature of the universe. Then you define science requirements that answer that question. Once you have science requirements, you can build a telescope. Well, once you have design of a telescope, and you build the telescope, then you test it on ground, because you're not just going to send it up there willy-nilly. You test it, you launch it, hope it survives the launch, and then you pray and you get some discoveries, right? So I'm going to dive into that process today. So if NASA's a factory that turns like questions into spacecrafts, tonight is your factory tour, and I'm your Willy Wonka tour guide. So to start, let's ask some big questions, right? A mission is something that answers one of these questions, and NASA missions answer huge questions about the universe. So for example, a big question would be, how old is the universe? That is a huge question that many cosmic microwave background explorers have probed before. Can anyone give me any other big questions in astronomy? Who has big questions about the universe? Big question?
Is astronomy in crisis?
Is it in crisis? That is a great question. And it has been caused by one of the new telescopes we've discussed here. That's great. That's a good answer. Does life exist on other planets? Aliens, that is a great question that has been tried to be answered by science fiction around through the test of time, human ingenuity. Yes? What is a feature of our universe? The future of our universe, right. How will our universe end? How will it die, right? Yeah, one last question.
Is it so convenient that Neil Armstrong spelled Neil A backwards spelled alien?
Right. Now that is the bigger question that I would have to ask Neil Armstrong's mother if she were here. Unfortunately, I don't have that capability. Although I am American, I'll just call home, right? Now these are great questions, right? So these are huge questions, and each of these questions can, maybe not Neil Armstrong's question, but each of these questions can be directly probed with a telescope, right? We can take these questions, build and design a telescope that will answer us these questions, right? So for example, with the James Webb Space Telescope, one of the largest questions is, how do the earliest galaxies form? And when do they form, right? Behind us is a simulation. I'll turn the lights off, I guess. There we go. Behind us is a simulation of many stars collapsing and forming into galaxies. This was done in a NASA supercomputer to form a galaxy kind of like the Milky Way, right? We want to understand how these form and use that in real data, not just simulations. We want to understand when. So we want to build a telescope that can help us understand this, right? So another larger question then is, what are the planets of atmospheres, right? Because we go back to that life question. If we have an exoplanet, so planets around other stars, and we want to understand what its atmosphere is like, we have to probe that with a telescope. So is it nitrogen and oxygen? Can we breathe like regular space, right? I can breathe in nitrogen and oxygen right here, but I can't breathe in water if my atmosphere is made of water. So we want to test what these worlds look like, right? So after we've asked our big questions, we have to turn that into science. And how do we do that? We create requirements. So requirements are just science in numbers. So we have to define the requirements of our telescope in numbers so we can try and answer those questions. So a simple analogy might be your phone camera, right? You have to choose, the manufacturer, Apple, has to choose how many pixels they want in their sensors, right? How big is the glass? How far can we zoom in? How far can we zoom out, right? These are requirements that are made by the manufacturer to answer some question that the user might want. And for astronomy, we can go back to James Webb. Big questions our big questions can be answered in infrared radiation. So this is one of the biggest design factors of the James Webb Space Telescope. So infrared radiation is light that is so red that you can't see it. Our eyes are not made to see infrared radiation. But if you've ever warmed your hands on a fire on a cold night, there's probably some hand warmers outside. It's quite cold today. You're feeling infrared radiation hitting your skin, and your hands start getting warm, right? So the earliest galaxies are so far stretched through the expansion of the universe that they're not invisible light anymore. We can't see them with our own eyes with telescopes like Hubble, which view in the optical wavelengths, right? They stretch into the infrared radiation. So we want a telescope, if we're going to answer our first question, to have infrared radiation. The second question, about how faint these galaxies are, we need a really, really big mirror to catch all that. And we have design trade-offs that we need to face, and these requirements lead us directly into these trade-offs. So step 3 would be these design trade-offs. Some of the biggest telescopes that we know need to be really cold and really large, right? Because if we're viewing a faint galaxy that's in the infrared light, so that light that's warm, heat means noise, because that heat gives off infrared radiation, which is not coming from our galaxy, but might be coming from the computer that's on the telescope, right? So we need to shield that from the cold. We also need to make it large so we can see our object, so much collecting area, so we can bring in all the light that we can. So we need to make trade-offs because in practicality, we can't have everything. So some of the largest trade-offs in mission design are performance, so how good is your telescope, cost, how much it costs, because everything costs money these days. And we have schedule as well. So how fast can this telescope be built? Will it be built in 30 years? Will it be built in 5? So we can actually explore these together. So I've made a quick demo here. So we have, perfect. So there's 3 trade-offs we have, right? We have cost, we have schedule, and we have performance. But you can only pick 2. So I want somebody from the crowd to pick 2, and we'll see what happens, okay? Let's see, what do you got? Cost and performance. So we want an expensive telescope. That's really nice, right? All right, let's see what happens. Okay, so you have a great telescope. It costs a buttload of money, but Congress said, yeah, go for it, right? But the issue is schedule. So you have to build a really expensive telescope, and really expensive stuff requires a lot of management and a lot of making sure that that money goes to the right places. And you also have a really strong telescope, so you really had to spend a lot of time building and designing that telescope to make sure it's really that good. So an example of this is the James Webb Space Telescope was actually supposed to be launched initially in 2007. And then it was delayed to 2011, further delayed to 2018, further delayed to 2021, right? We got the money from Congress, it was about $10 billion, and we got a really excellent instrument, but it took over 20 years to build. And that's kind of not acceptable in these mission development pipelines. So we can reset it. Who wants to give me another one? Up there. Cost and schedule, right. So we got the money from Congress. They said yes, and we got a schedule. It's actually on time. Our issue is performance, right? Because we're doing it fast, and because we're doing it with the money we have, we can't actually make our instrument as good as if we wanted it if we had $5 billion more, or if we had 10 more years to actually build that telescope, right? And someone want to give me the last trade-off? Right there? Good stuff. All right, so now our issue is cost, right? So we have a really nice telescope, and we took actually a decent amount of time to get up, but it was okay. But the issue here was cost overruns, right? So we launched the Hubble Space Telescope into space in the late 80s, 90s, and an issue that immediately happened was the mirror was wrong. They shaved down the mirror. It was the smoothest object ever created, and it was the wrong conic shape. So it was focusing the wrong stuff. So they had to send a space shuttle with 5 astronauts. I actually met the astronaut, and he was a professor at MIT. I didn't go there, but I was in Boston. And he gave a lecture about servicing the Hubble mission, right? But that cost hundreds of millions of dollars. So it cost extra money to service and repair and give Hubble a pair of glasses to make the discovery that it actually needed to do, right? So you can see in this design, you have all of these trade-offs, and you can't have everything, right? But we can try our best. So that's what we're trying to do with the James Webb Telescope. So for example, all right, here we go. Boom. So you want a really big mirror. We knew that the next telescope after Hubble wanted to be really big, but it still has to fit in a rocket to get into space. So what did engineers do? They folded it. They folded it together. And that's how we have this segmented design instead of one circular mirror. So if you can see in the middle figure right here, Hubble had to fit inside of a space shuttle. There's no folding, no bending, nothing. But James Webb has to fit in the top of an Ariane 5 rocket, which means it folds up in the middle. And you have to make you want to make the mirror as big as possible so you can collect as much light as you can in space, but you still have to make it fit in the rocket or else it's not going to get into space in the first place, right? So that's a design trade-off. And a second trade-off is we want it to be really cold, right? So James Webb is actually 1 million miles away from Earth. They launched it and it flew away. But 1 million miles away is too far for humans to service. Hubble is only 300 miles in Earth. It was reachable by a space shuttle. And they actually put the glasses on Hubble to fix it, right? You can't do that with James Webb. So James Webb is in L2 orbit. It sits behind the Earth, which is in the center there. And it's got a massive silver sun shield to block all of that heat. Because remember, we're trying to look in infrared radiation, so that's that heat. We don't want anything coming out from the sun. So it's super far away from Earth, which is one, more expensive. You have to spend more rocket fuel to get to that place. And it's also less serviceable. And Hubble, here's a picture of Hubble being serviced, right? So it had a different trade-off. It's not viewing in the infrared, so it can take heat. Its electronics can be hot. It views in visible wavelengths like we do with glasses in green, blue, and red, et cetera. And we put it 300 miles from us, which is really accessible. Accessible with a few $100 million. And we repaired it 5 separate times. But if JWST got damaged, It's game over. It's a million miles away. We can't fix it. So these are kind of the design trade-offs that you have to think about when you're actually building a telescope of something of this scale, this many people, this much money, right? So if you're happy with your trade-offs, say we had a cost and a performance, right? But it's going to take a while. That's fine. That's kind of what JWST did. So now you have it. You're going to have to build it, right? So NASA assembles thousands of unique parts in extremely precise and extremely clean environments. This is an example of the upcoming Roman Space Telescope being assembled in Goddard Space Flight Center in Virginia. You can see everyone working with the ants, rolling around the clean room, assembling this telescope. This process takes years. It takes billions of dollars for these most expensive flagship telescopes. And if one part is built slightly wrong, one contractor that you didn't know, you didn't trust, builds a screw that's wrong, and it fails when it launches, game over, right? So you have to be extremely precise and extremely efficient to assemble these devices in time, on budget, etc. So here's an example of JWST. It's got its classic hexagonal segment mirror, some B-rolls of it being built inside these clean rooms in Goddard. Here's it partially assembled. Here's the full thing inside of the clean room in its glory. This is before it was folded up and sent into space. So this is the best look we got at it, because once it went away, it got folded in the telescope, launched in the rocket, and we can't see it anymore. It only takes data from us. And now, once you build it, you got to send it away, right? But you're not just going to send it immediately. You're going to test it on the ground first. Because remember, with James Webb, we can't repair that once it's in space. So if anything's going to break, we better know about it now, when it's on the ground, when it's close to humans to fix. So you got to test, and test more, right? So once you launch a telescope into space, you rarely have an opportunity to fix that problem. So what you do is you test over and over and over again. So 3 of the major test diagnostics is vibration tests. So you put the telescope on a big platter and you shake it really, really, really hard until something falls off. And once the first thing falls off, you stop the test. You say, this is a big shake. Oh my goodness, it's almost a rocket launch. And one thing fell off. Oh, that's 6 months delayed, because you have to see it bounced off this, it scratched that, right? So this is what happened with the James Webb Telescope. During the first shake test, it delayed the project by 6 months because a few screws fell loose. And that would have happened on the rocket if we had not tested for it. But we tested for it, we fixed it, did another shake test, everything passed. The vibrations for the rocket launch were good. All right, next test, does it survive in space? So here, we're breathing in air. There's molecules all around us, but in space, there's nothing. Not air, not oxygen, not hydrogen, nothing. It's a vacuum. So you take all the air and you suck it out. And you can do this on Earth. You put it in a big room, you close all the doors really tight, and you suck out all the air to simulate what it would be like in space. And you can do that at the same time by dropping the temperature. So space is really cold. And remember, we want our telescope to work in really cold environments because our telescope is seeing an infrared light. So we get down all the way to 20 degrees Kelvin, or 20 degrees Kelvin, or negative 250 degrees Celsius. So that's much colder than tonight. And test to see if the computers don't freeze, right? We need the computers to work at 20 degrees, right? So this is an example of James Webb in Houston going into its 3-month hibernation. So when you enter this massive vacuum chamber at the Space Flight Center, it cools down for a month. It operates for 30 days. So you can see in space, in this cold, it would operate like this. We would hope it would look like that. And then you take 30 days to warm it back up again and let all the air back in. So that's almost 3-month hibernation. But not everything goes to plan. And when the air got sucked out of the chamber and it got really cold, there was still some stuff left because you can't make a perfect vacuum. We try our best, humans, we do that as best we can. And stuff fell onto the mirror of the telescope. But the mirror has to be really, really smooth or else we can't see the light we need to see. So what they had to do was manually brush off the dust. And I'll show you some footage of that happening.
A decision was made to clean the mirrors. And you look at multi-million-dollar beryllium, gold-coated beryllium mirrors. You're not using squeegee and some Windex.
So we rotated it so the gold primary mirror was cupped down. The big fear is that, especially on a coated optic, that through cleaning it, we're going to damage the coating or scratch the mirror or put some other substance on the mirror from what we're using to clean.
Larkin and his group from Ball went in a prone position with a very special kind of brush, an IPA, where they cleaned all of the primary and the secondary mirror with tiny little brush strokes. Maybe each stroke was a half an inch to an inch. And so it was incredibly detailed work that took a while.
Right? So this was a real issue that happened with James Webb. And they had to lie down, take a brush, go up and down and up and down and up and down for weeks to fix this kind of stuff. And that caused a further delay, right? That's why our James Webb Telescope was not on time, unfortunately. But it was cleaned. The engineers got the smoothest mirror that they wanted. And once that's time, it's time to go, right? So the most nerve-wracking experience of this entire process is launch, right? And deployment. Everything built to this. You've strapped your really delicate rocket, that's multi-billion-dollar machine, to 700 megatons or kilotons of controlled explosives, right? And it's time for that bumpy ride that we shook for, right? So for JWST, that's what this looked like in French.
7, 6, 5, 4, 3, 2, unité, top.
And we have engine start.
Our telescope's folded up there at the top. There it goes.
Decollage.
No screws falling off right now.
The rainforest to the edge of time itself.
Yeah.
James Webb begins a voyage back to the birth of the universe.
So, great question. This telescope wasn't actually launched in the United States. It was launched in partnership with the European Space Agency with France on their Ariane 5 rocket. And it was launched in the French Guiana. So, that is why, yeah, they shipped it on a shipping container from California where it was assembled all the way to French Guiana, launched it in this rocket at their space facility. So that's why I said before also, NASA has incredible international partnerships that are crucial for missions to work like this, right? We don't have a space shuttle anymore. It's really hard for us to launch these big stuff into orbit nowadays. So we asked France, called up our old buddy, old pal, to create a launch, right? And you don't have to just launch. Now we're in space. But remember, how did we get inside the rocket? We had to fold our mirror. We folded it up inside. And this was the biggest breathtaking moment of probably the history of NASA, in my opinion, right? So it's all bundled up. We have 15 years delayed, over $10 billion, millions of man hours put into this telescope, and it needs to unfold on its own in space. There's no one pulling these shields out, right? So for James Webb, it had 344 single critical point failure mechanisms. 344 single stages where if one thing went wrong, the whole mission was gone. It was all toast. $10 billion wasted, dozens of years wasted. If this had failed, Congress would not have been happy. They want their $10 billion back. They think it's a failure. NASA might have been gutted or defunded. This was a huge moment. If a single hole appeared in the sun shield, mission over. Single pin releasing that deployment failed, mission over. If that tripod was locked in an inch off, mission over, right? These are critical deployments. But James Webb did it. It got to L2, got 1 million miles away from us, it expanded. Every single point of failure was tested before. It worked on the ground, and we sent it to L2 orbit 1 million miles away, and it worked. And once you're there, you got to do some calibration, because once you get it out the box, you get a brand new car, the manufacturer's not sending it without testing the engine, right? They're going to make sure it works, runs smoothly, it's all focused in, everything's dialed in, so you just have an easy experience using it. So the telescope reached its unfolded state, resting orbit, and now it can undergo months of calibration and testing. So this segmented mirror, they're all in random shapes, right? But we want to focus it onto this secondary mirror, which is at the top. Here, I'll put it down here, put that light down. You can see it's all trying to focus in the light. You can see the actual image on the right. And now that all the mirrors are focused and aligned, it sends that light down into the detector. And then we get a sensed image, right? And all these 18 different mirror segments are really stacking to create one super image, or a co-edition, as we call them in astronomy. And once, this is essentially James Webb putting its glasses on. And once we put its glasses on, it can see really well. And James Webb now gets to reap the benefits of all these years of preparation, all these billions of dollars in planning, and now we operate and we discover. So this is an example of one of the first images taken by James Webb. It's a nebula, absolute incredible resolution, groundbreaking science. So as astronomers, get to use this telescope. So it's just like that manufacturer sending the car, or your iPhone manufacturer sending you the iPhone after calibrating everything, right? I get to write proposals to NASA, so do professors here at Cambridge, so do people around the world, to say, I want to look at X with your telescope. It's important because of Y, and it'll impact science because of Z. And thousands of astronomers around the globe, and every single continent in the world, submit proposals every year to James Webb to get time to observe what they want to observe with this incredible instrument. And James Webb is especially prevalent at Cambridge, where lots of professors have made incredible discoveries about exotic objects and incredible stuff in space, right? So now that it's in space, we've completed our loop, 1 through 7, we're done. But the whole point of this is discover science, right? So we can go back to our questions in the first place. So what was our first question? So how and when did the first galaxies form? So James Webb took its first deep field in the S-Max galaxy cluster. So what you're looking at in the center is a cluster of galaxies. And you can see those extremely bendy galaxies coming around, forming a ring towards the center. That's called gravitational lensing. So that's when Einstein's equations, they predict that really heavy objects can bend light. So we have a space-time curvature, and the light falls into that well and rides that curve. And you end up getting a beautifully curved image like this, right? And in this field, there's a bunch of little tiny red objects at the bottom and scattered around here. And these galaxies that we found are too early, right? I heard a question about a crisis in cosmology. We found galaxies that are too early, that our models predicted. We looked at our best data from Hubble Space Telescope, looked at our best data from ground-based observations, and we said galaxies should form at this time. And they didn't. They formed earlier, and we didn't know that until the James Webb Space Telescope happened, right? So we answered this question, well, when and how? 500 million years ago was when roughly the first galaxy formed, as seen by Webb. Could be earlier if we had a better telescope, but this is what we got right now. It's incredible. And it's upheaving modern cosmology, right? It's not a crisis necessarily, because then we'll lose our jobs. But it's a really big question that everyone's going back to the drawing board on. Our second question, exoplanet atmospheres. Could there be life, right? How do we know that? How can we detect that? So if a planet passes in front of a star, it blocks some of that light. But around a planet is an atmosphere. And that light hits the planet, we can't see that. But it passes through the atmosphere in different wavelengths for different molecules. So every single molecule has its own fingerprint that we can detect. And that's called spectroscopy. And when we look at that for James Webb, for example, this is a Jupiter-like planet. It's called WASP 39b. We can see that this atmosphere has carbon monoxide. It's got sodium, it's got carbon dioxide, it's got water. You know, it's not going to be a life-forming planet because it's a gas giant like Jupiter, but we can do decoding and forensics on this data and see what is inside an atmosphere that is trillions and trillions and trillions of miles away with this incredible telescope. And sometimes you come in with certain questions and you get surprised. There's a new question that you didn't even think to ask. For example, in 2024, the first evidence of these, quote, little red dots was discovered. And I'll tell you what they are. We don't know. They just started appearing in the back of our images. They were really far away. They're really bright. They don't emit in what we think they should. It just stunned. It's totally stunned astronomers. I bet a third of Cambridge University astronomy is working on this problem right now. We don't know what they are. They might be supermassive black holes that are forming very early in the universe. They might be stars with 1 million solar masses that we've never seen before, population 3. Who's heard of that? We don't know. But that's the exciting point of this science, right? It pushes the frontier of our knowledge. We discovered galaxies that were too early. We discovered chemicals in foreign atmospheres. We discovered things we don't even know what to call, so we call them little red dots, because they appear as little red dots on our computer screens. And that drives the next cycle of development, right? That's another question. What is a little red dot, right? How can we explore that? You build your next telescope, right? So if we had a factory of questions to discover the next set of sciences, right? NASA's next questions, for example, are can we find Earth 2.0? Can I find and directly image a planet that looks like Earth? Can I know what dark matter is? Dark matter makes up 25% of the universe's energy mass, right? 25% of the universe, we have no clue what it is. Those are more questions that we can ask. And when I was at JPL this summer, I was working on the Habitable Worlds Observatory, which is currently in steps 2 and steps 3 of the factory process. So currently we're designing it, And we're giving those questions and making those requirements, saying, I want the telescope to be this stable. I want the telescope to be this precise. I want this telescope to be, et cetera. Trying to answer these questions. Here's a sneak peek at what these telescopes look like. So there's currently 3 designs. We took back the shields to see them. The first design, EAC-1, is kind of like James Webb. You can see that segmented mirror, but it's got an off-axis mirror, so it doesn't get those struts. The second one's kind of like Hubble. It's a little circle. And the third one is kind of a combination of both. It's got segments and it's circular, right? So these 3 concepts are currently being debated among physicists at NASA. Which one's going to give us the best performance? Which one's going to answer our questions? Which one we can simulate as much as we want? What these telescopes will see, how they will perform in space, what designs we can make them perform, right? And that's exactly what I did at the Jet Propulsion Laboratory. I was creating simulations to answer the dark matter question. So if we remember back to that gravitational lensing argument where light gets bent by galaxies, by really, really heavy objects, if you have a galaxy that's right down the barrel, so if you see it right here, there's a galaxy right here, you get a really big ring of the galaxy behind because that light gets bent in all directions around. And you can look for dark matter around these galaxies with that bending. And my work was simulating the 3 telescopes here and simulating what they would see. And this is going to inform the engineering team saying, hey, I need my telescope to be this big. I need my telescope to be this stable. I need all of that kind of stuff to build that telescope. And as of last week, there's $150 million in funding for exploratory work, not even building the telescope yet. We're just going to simulate everything for this telescope design, and it might come into fruition in the next 10 years or so. Maybe when some of you guys are here doing your PhDs at Cambridge, right? You'll be answering these questions with these telescopes. So for an example of how this works, right? So that's a planet we want to see, Earth 2.0, but it's really far away. You know, it's right next to a really bright star, and planets don't really emit light, stars do. So how are we going to do that? So we need really, really stable optics. These mirrors need to be really, really, really stable, and they need to be high contrast. So you need to see something, and you need to block it out. So if you've ever been outside on a sunny day, quite rare in England, you put your head over your head like this, you block out the sun, you can see more, right? That's why we wear a baseball cap. But in space science, you can't do that you can only do it with precise optics, and you can only do that with an extreme contrast ratio that's unimaginable. So if I had to tell you in a comparison, James Webb has one of these light blockers on its telescope. And if it could look at a lighthouse and block out the lighthouse's light and see a firefly right next to it. And that's an incredible piece of science. You know, that's the cutting edge of engineering. To see it Earth 2.0, 30 light years away, we would need a contrast ratio of blocking out that lighthouse and seeing a single cell of bioluminescent algae, right? That's insane. We don't know how to do that. It doesn't exist. But NASA's working hard. My advisor for one of them is doing engineering requirements to try and make this a possibility and try and fly something like that. It's an incredibly tough requirement. But through years of engineering and manpower and money, we get through these tough engineering problems. And that kind of leads me back to the factory never really stops, right? You have a new telescope that makes a new discovery, which gives you a new question. And then you build a new telescope to probe that new question. And it goes on and on and on again. So both at NASA and here at the Institute of Astronomy, we ask these big questions about the universe, hoping to learn something and turn them into answers. Discovering new realities that will hopefully solve crises in cosmology, find out why Neil Armstrong's name is Neil A, alien backwards, or all this kind of stuff. So that's my talk. Thank you, guys.
There's a hand up already. Do you have to do some questions?
Yes, let's do some questions.
Okay, look, you seem to be the keenest.
Gotcha.
With all of these questions, where is NASA hoping to take all the answers and questions to a certain point? What big question are they trying to answer with all these little questions and little fragments?
Yeah, that's a great question. I think one of the biggest problems in all of physics and all of the universe is the issue between general relativity, so Einstein, and quantum mechanics. So we have a theory that predicts stuff at really, really small scales. So atoms, electrons, they work really well. But if you add gravity to the equation, everything breaks. It doesn't work. And Einstein, if you predict gravity at really big scales, planets, galaxies, works perfectly fine. You see all that gravitational lensing? Exactly predicted by Einstein. But when you put quantum mechanics at a big scale, it doesn't work, right? So if we understand how our universe is born, how it accelerates, how fast it's moving, how it will end, maybe we can reverse engineer our question to our theory of everything, right? We want a theory, some set of equations, some mathematical algorithm that can describe everything, big to small, because everything happens, right? There's got to be something that describes the universe. We have one for really, really small, one for really, really big. They work really well in their regimes. Einstein's cheeky. He hasn't been proved wrong yet. But maybe all these little questions can add our meaning to that big question. That's kind of my best answer for you there. Yeah.
So, forgive my ignorance here, but what I deduce from what you've told us so far is that the way in which you're looking at things is highly light-oriented.
Yeah.
But surely there are multiple other forms of radiation that yield other observations, as it were.
Yeah.
Light does not. So what is the reason why everything is so highly light-oriented?
Yeah, so I would say that there are almost every signal that we get from the universe is light. So that goes from radio, and you can't build a radio telescope in space because the wavelength of light is so long that you need to build a big dish on the ground. So it goes from radio all the way to gamma. And that is a huge spectrum with tons of information that we can do. But for example, there's a few signals that aren't light-based. For example, gravitational waves. They were discovered in 2014 when two black holes merged, and Einstein predicted 100 years ago that space itself would ripple, right? That's information that we can get and we can observe from the ground. But in terms of other modalities, there isn't much else there besides light, because that's all we can actually see. So you can put a telescope in the sky like Hubble that views in our visible wavelengths. You can put one in infrared like James Webb. You can put one in ultraviolet. You can put one in whatever you want. You know, any type of that wavelength regime to hopefully grab all the information that we can about that universe, because we can't actually go to these places to check what they actually are, you know? So I think the information paradigm is hard to get past, but I hope that answers your question. Yeah?
If the whole universe is 25% dark matter, is it like another form of matter that isn't just normal matter?
Yes. So we don't know what it is yet, right? So that's a great question. It actually ties into this question as well. We can't see it with light. Dark matter is dark because we can't see it, but we know it has gravity. So we've looked at images like this one back here. Let me put it right here. And we saw the bending of light, but when we counted all the stars and all the galaxies that were there was too much matter. There was matter that we couldn't count in our stars. It was extra stuff that must have had gravity, or else it wouldn't have bent this much, because Einstein's equations predict exactly the curvature of these bends up here. And there's extra matter that we can't understand. We don't know why it's there. But the only explanation is there's some matter that doesn't interact with light, so that's another information issue there. It just passes right through. That or our equations of gravity are wrong, but Einstein's pretty tough to beat, as I keep saying, right? So we don't know what dark matter is yet, but I showed in my science case over the summer that hopefully with a really strong telescope like the Habitable Worlds Observatory, we might be able to actually directly probe that. Because if you can count the number of little bends that are too much matter, and you can count them at a really small regime, where this dark matter is really small instead of really big, the theories that we have, that all the math guys that are in the department across the street over there in the theoretical math department, which I'm not in, can do, they will predict very different things. Some theories of dark matter say there's 1,000 of these tiny subhalos. Some say there's 0. So we just try and find anything that we can directly observe and directly probe and turn it into a telescope and an observation. So hope that answers your question. Yes?
Time work differently in space?
Time works differently when you're moving really fast or you're really heavy. Those are the two places where time works differently. So if you've ever seen Interstellar, when they get really close to that black hole, there's tons of gravity pulling down, and that changes the fabric of space-time. And for Matthew McConaughey, 100 years passes, and his daughter completely grows up while he's in that black hole area, right? Or you can move really, really, really fast, close to the speed of light, and then it looks like your time is slowing down, and you're moving super, super slowly throughout the universe, right? That's what Einstein predicted, and his equations, time and time again, they're right. So time does work differently in space, but it's more like how fast you're moving. So an astronaut moves very fast in space, but not that fast, only a few thousand miles an hour. And he will age nanoseconds longer if he spends 6 months in space than us, because we're not moving that fast, right? But you have to be moving very, very close to the speed of light for time to actually matter like that. So that's how time moves in space. Yeah?
You use
Yeah, so there's a board committee at NASA. They review lots of scientists, just like the ones and the professors who just happen to not work at a university but happen to work at NASA. They review the science for its merits. They compare to other literature. They say, if this question is really answered, can we actually gain new understanding? Also, if this question can be probed at all, whether their theory, like my theory that there's going to be this much dark matter in this galaxy might be true, might be not, should be backed up by some theory, some previous research that informs the next proposal, kind of. So it's kind of a review process. You pass a blanket review. Are you a scientist at all? Are you going to submit something that's completely phony? Does it have merit? Will it work with this instrument? Because you have to propose a plan for the instrument itself. Because I'm not going to say to James Webb, hey, I want you to view in blue wavelengths. It can't do that, right? So it's like a tiered step system of how to do proposals. I actually haven't written a proposal myself yet. I'm only a first year PhD, but plan to in the spring. So we'll see how it goes. Fingers crossed. Sorry? Yeah, so the James Webb Telescope is so oversubscribed. It's the hottest piece of instrument in astronomy because you want to take photos like that, don't you? So for every 9 proposals that are submitted, only 1 gets accepted. So it's a crazy oversubscription rate. But if you keep applying, Hubble's been open for 33 years. You can hopefully get one at some point, right?
So yeah, professional astronomers tend to approach have like a carpet bombing approach. You like everything a whole bunch of times, and if you write 20 proposals in a year, you might get like 3 or 4 or 5 back, and then that's a good year, right?
Yeah, another question.
James Webb Telescope is basically Hubble Space Telescope 2.0. So what's the point of the Hubble Space Telescope?
So it's close to Hubble 2.0, but not necessarily. So remember how they view in different wavelengths? That gives us different information about astronomy. Because certain stars emit green wavelengths, but not infrared wavelengths, right? And certain ones only do in the infrared. And the galaxies that are really, really far away, they get stretched so much that you can't see it with Hubble. Hubble doesn't even know it exists because it can't look in that far of infrared. So it's kind of separate. The Hab Worlds Observatory will have an imager that is in the visible wavelengths. So the Hab Worlds Observatory over here. It will be in the visible wavelengths. So it's kind of a super Hubble. And the point of a super Hubble is that Hubble Space Telescope was built in the 80s. And we're a modern society with modern technology. We can make a telescope that's 50 years newer, 50 years better of our current technological advancements. That's the point of making a super Hubble, right? You get more pixels, you get more data back into your telescope, and you get a new discovery, hopefully. Because Hubble can't look at this small part of dark matter, for example. But this Hab Worlds Observatory has a new camera that's really, really advanced because of the advancements in technology and chip design in the last 50 years, that it allows for this stuff to be probed. So bigger, better, badder. That's the goal for every telescope these days. So.
Okay, time for one last question, maybe. Would you have one last question?
Yeah.
You say NASA's working on whatever's next.
Sure.
Is there other space agencies, such as like SpaceX, that could potentially beat you to that, or do you work alongside them to, find new ways together, or are you kind of competing against them?
Yeah, it's a great question. So I'll say that other space agencies, like the European Space Agency, the Japanese Space Agency, Chinese Space Agency, they all have their own telescopes. And as I said before, these missions are not just NASA. Like I say NASA's Hubble Space Telescope or NASA's Webb Space Telescope because they're the primary providers of the funds and the instruments, but one of the James Webb instruments was designed in Canada, right? So it's international collaboration like crazy. Industry partners like SpaceX, they tend to make rockets. So SpaceX makes rockets, they send the satellites up. So the Hab Worlds Observatory, as I saw in a design document 6 months ago, is currently planned to be launched in a SpaceX rocket, right? We don't have NASA takes, it's too expensive to send ourselves a rocket into space like that. But SpaceX has, through commercialization, through capitalism, has designed a rocket so efficient that it's pretty cheap to actually throw it into space. So kind of working with industry partners is very important for that. I don't see a future where industry partners build telescopes because for stockholders, for investors, what economic return does the Hubble have, right? It's for science, it's for kind of the common good more that. The economic returns are really building and engineering and launching, right? There's a lot of money that goes into research, a lot of money that goes into these technologies that have trickle-down effects, and because it's publicly funded with taxpayer dollars, that's all public. It's all free for everyone to use, industry and NASA alike. So I wouldn't see them making a telescope, but I do see commercialization in terms of launching things into space happening like crazy in the next 10 years especially. So
Okay, I don't think there's any more time for questions. The sky is clear. We don't have any stars. So just a little bit of housekeeping before we go out. So what you're going to find is on the lawn, in the main kind of observing area, there'll be some telescopes and some screens where you watch things. There'll be a couple of domes open, so for you to actually look through telescopes physically. One of them will be the big old dome on the lawn that you can't miss it. There's another dome through the trees, which there should be a red rope light leading you to. Don't forget to visit that one. The students get lonely there. And they should be all looking at different things to give you a good experience. So can we thank George again?
Thank you, guys.